The first subroutine we need here, which we also have utilized in the previous lesson, is HETVAL. It is a useful tool that lets us specify the heat flux generated internally. HETVAL acts as a bridge that takes information from Abaqus, computes the heat flux, and then sends the necessary data back to Abaqus. We have used it to compute the heat flux during the curing process in this lesson. We are here to guide you through writing the subroutine step by step for the goals in this lesson. But for more detailed information about this subroutine, check the Abaqus User Subroutine Reference Manual. Next, go to the User Subroutine section, choose Abaqus Standard Subroutines, and explore the details available in the HETVAL section. The second subroutine, DISP, remains the same as in the previous lesson. It is used to define or modify boundary conditions, particularly to apply the cure temperature cycle. Since it has not changed from the previous lesson, we won't describe it again here. However, for more details about this subroutine, you can refer to the Abaqus User Subroutine Reference Manual. Then navigate to the User Subroutines and select the Abaqus Standard Subroutines section. Look into the contents available in the DISP section for further details. The two subroutines we have talked about were used in Lesson 1 for thermochemical analysis. However, for the thermomechanical analysis, in this lesson we need extra subroutines. The new subroutine we need, UEXPAN, is designed to calculate incremental thermal strains in Abaqus. These strains can be determined based on temperature, field variables, or state variables. So the HETVAL subroutine is helpful for modeling complex scenarios when thermal strains are influenced by temperature or state variables. This feature does what we need for calculating the thermal expansion and shrinkage strains in composites during the curing process. We will guide you on writing the UEXPAN subroutine for this lesson during workshops. However, for more detailed information, you can see the Abaqus User Subroutine Reference Manual. In the manual, navigate User Subroutines, choose the Abaqus Standard Subroutines section, and review the information provided in the UEXPAN section. The fourth subroutine required for this lesson is USDFLD. Many Abaqus subroutine users are already familiar with this subroutine, and it has multiple general applications. It enables us to set field variables based on time or material pointed quantities. So we can use it to introduce material properties that depend on the solution. Its main function for us is updating state variables such as the degree of cure and cure rate and transferring them to other subroutines. During the workshops, we will guide you step by step in the writing subroutine for the objectives of this lesson. However, if you want to learn more about this topic, you can check the Abaqus User Subroutine Reference Manual for additional information. Then go to the User Subroutine, select the Abaqus Standard Subroutine section, and explore the information provided in the USDFLD section. The last subroutine we need is called UMAT. It is a tool that allows users to define the mechanical behavior of a material, particularly when the default Abaqus library models are not suitable. This subroutine enables the utilization of state variables to define material properties. Such a feature is essential for simulating the curing process. UMAT helps us in defining a model that describes the changes in the resin's modulus of elasticity during the curing process. In the workshops, we will guide you step by step in writing the subroutine to define composite properties during the curing process. But if you feel you need more information about this subroutine, check the Abaqus User Subroutine Reference Manual. Next, go to the User Subroutine, choose the Abaqus Standard Subroutine section, and explore in details in the UMAT section. Now that you have understood the purpose of using these subroutines in this lesson, you may want to know how they work together to solve a problem. Do you think these subroutines interact with each other or not? This is a crucial topic that we will explore now. We have numerous Abaqus subroutines that can interact with each other. But what does this interaction mean? It is very simple. Imagine a situation where state variable is updated within one subroutine. Then the updated state variable is utilized or referenced in another subroutine. This demonstrates how different subroutines in Abaqus interact with each other. Note that this doesn't apply to all subroutines. Some of them work independently, not using field or state variables, and therefore do not interact with other subroutines. The Abaqus documentation details how its subroutines interact and the sequence in which they are called. Specifically, the Abaqus user subroutines reference manual explicitly outlines the order of subroutines execution. You can refer to it to understand how multiple subroutines interact with each other in a problem. Due to the importance of this topic in this lesson, we have referred to the Abaqus manual before starting to write the subroutines. The first subroutine we have used is DISP, which solely depends on time and doesn't rely on other subroutines. It works independently in our work. But what about the other subroutines? They work together since they all rely on state variables. But what is their order of call? We will say. Based on the documentation, HETVAL is called after USDFLD, UMAT, and UEXPAN subroutines. Therefore, it utilizes the latest values of state variables from other subroutines. UMAT is called before HETVAL following USDFLD and UEXPAN. EXPAN subroutine is called after USDFLD. According to the sequence of subroutine calls, USDFLD takes the initial action in our work. In USDFLD, we will update state variables such as the degree of cure and cure rate. The updated values will be utilized by subsequent subroutines. Cure rate information will then be sent to UEXPAN, which computes cure shrinkage and thermal expansion increments. Subsequently, UMAT incorporates the degree of cure to calculate the Jacobian matrix and stress. Finally, HETVAL uses the cure rate and the degree of cure to determine the heat flux. As previously mentioned, DISP operates independently in this lesson. It applies the temperature boundary condition without relying on any state or field variables. Here we have just reviewed the role of each subroutine to explain why multiple subroutines are used in this lesson. In the provided workshops, we will offer detailed guidance of how to write these subroutines step by step.